Welcome, Professor Bright here, and we're going to look at solving exponential equations, logarithmic equations, and then applications in this next video series. So a lot of these we've seen already, but we are going to kind of see them in different ways and in more general settings too. So just know that if this seems familiar, that's probably because it kind of is. Okay, so we've encountered exponential equations, which is what this video is going to work or look at first. And so we've seen examples like these, where we have 5 to the 3x minus 1 is equal to 5 to the 2x. And so then what we've done to solve this is, well, we recognize that 25 is really the same as 5 squared, so then we can write the right hand side here as 5 squared to the 2x, and then this left side is just still 5 to the 3x minus 1, and then 5 to the 3x minus 1 is equal to 5 to the multiplying exponents by properties of exponents, so 5 to the 4x on the right side. And then we notice that this is an instance where we can apply that one-to-one property and say, well, this is, since the bases are the same, then the exponents must be the same. So then 3x minus 1 is equal to 4x, and then subtract 3x on both sides, and negative 1 is equal to x, and we're done. Okay, and then this next one, similar to what we've seen before, our intuition might say, oh, let's isolate the exponential. So if we do that, we get 4 to the 3x minus 2 is equal to 9. And then, now this is one of those scenarios that we found ourselves in early on in this chapter, where we said, oh, look, this is an equation. We don't know how to solve it. So rather than try and struggle with this, we're just going to define our way out and look at the inverse. And that idea introduced logarithm. So we would say this is the same as log base 4 of 9 is equal to 3x minus 2. And then add 2, divide by 3 to solve this formally. And we end up with log base 4 of 9 plus 2 all over 3 would be the value of x. Okay, and so this just the key points in each of these aren't necessarily the algebra. It's in this first one, it's getting to same bases, and in the second one, it's the process of translating from exponential form to logarithmic form, using the tattoo, as it were. Okay, so we've seen these to some degree, maybe not exactly like this, but we've seen those strategies. And as I mentioned, the first one used this injective property, where if we had same bases, right, then we just set the exponents equal. And so we focus on this way. In the next video, we'll see the other representation of the injective function. And the second method, though, that one we've kind of seen before, but it maybe didn't appear in exactly that form, but it used what we might think of as more of a general approach. Okay, and when we solve exponential functions, generally what we end up trying to do is first isolate the exponential. So that was my very first step of, adding 7 to both sides. That was isolating the exponential. And then, now I didn't do this in the above example. We certainly could. We want to take a logarithm of the same base to both sides. Now, if I were to do that up top, I'll show you that. What I would end up doing is something like, so from this, I could do like a natural log of both sides. So it'd be natural log of 4 to the 3x minus 2 is equal to natural log of 9. I could do common log, whatever. I could also happen to choose log base 4. That would be fine as well. Okay. And then next, after this, we would likely have to use the power property. Okay, that's why we're doing this after learning about properties of logarithms. So then up here, I would have to bring the 3x minus 2 out in front, and then this would be times natural log of 4 is equal to natural log of 9. Okay, and then really from after we do that, then we would solve as normal. Okay, so this would be the general approach. So isolate the exponential, log both sides, apply the power property, and then solve. So for example, in this next equation, I'm going to kind of try and follow this general approach. So I need to isolate the exponential. Here's the exponential. Subtract 4 from both sides. E to the 4x minus 1 is equal to 13. And then log both sides. Natural log of e to the 4x minus 1. Now I chose natural log. You could have chosen a different one. Okay. 13, and then here the reason I'm choosing natural log is really nice because after I bring the exponent down, I'm left with natural log of e, which just reduces to 1, and then that makes my solving process even quicker, because then it's just 4x minus 1 is equal to natural log of 13, and then add 1 divided by 4, x ends up being natural log of 13 plus 1 all over 4. And I'm done with that one. Okay? Now this next one, it's going to get a little bit messy, so buckle up. So again, I need to isolate the exponential. Well, the thing is, they're both isolated. But which one am I going to use? Which one am I thinking of as the exponential? And the answer is, So I kind of have to skip number 1 when there's two exponentials appearing of different bases. But I'm still going to work through my general process. I'm going to apply a logarithm of the same base to both sides. So which one is it? Well, take your pick. I'm going to change from my standard of using natural log to using common log. And so I'd get 3 to the 5x minus 6 is equal to log of 2 to the 4x minus 1. Okay, and so from here I have to bring the exponents down, so I'd have 5x minus 6 all times log of 3 is equal to 4x minus 1 parentheses log of 2. Okay, now this is where it gets messy. We need to think of this log 3 and log 2 as a number. So for all intents and purposes, 3 and 2-ish. So then if this is just a number, you can distribute that, right? So you'd have 5 log 3 times x minus 6 log 3. And then distributing the log 2 in the same manner, you end up with 4 log 2 times x, and then minus log 2. Now I need to collect all the things with x's and all the non-x's, and so I'm going to skip a little bit of work here. I encourage you to fill in the dots, and if I get the x's on the same side, I would be able to factor out the x's, and I'd have 5 log 3 minus 4 log 2 after I factor it out, and then on the other side I'd have 6 log 3 minus log 2, and then solving finally we get x is equal to 6 log 3 minus log 2 all over 5 log 3 minus 4 log 2. Now I will add a little asterisk with this and say that I got a little sloppy with my notation, like I should have all these 3's and 2's in parentheses, but this is the answer. Okay, so the algebra here gets to be a little bit confusing when you have exponentials of the different base on both sides. If you wanted to, something that would make your life a little easier is apply a logarithm. Again, you can apply any log that you want, maybe pick a convenient base. So instead of log base 10, use maybe log base 3, and then those end up canceling, so like you have a little less to work with, but you don't have to. It would just make your life easier. Okay, so this first video is a little bit longer, but it introduces the general approach to solving exponential equations. So isolate the exponential, log both sides, apply the power property, and then solve as needed.